recorded some homework problems?
I recorded some. I did not get to record all of them. I've kind of been buried with 211 stuff.
Yeah,
So
yeah,
I have
I
not
noticed.
finished that recording session, and I really
Yeah.
apologize to students.
No, you don't have to apologize for anything. Um, uh, you've gone above and beyond. But I thought it might be good, actually. People were kind of clamoring a little bit for some more problem session type stuff. Um, and I did have a look at the last homework, and I thought, especially since I haven't really been having office hours uh, since I've been sick, that maybe this would be best rather than talking about the wonders of particle physics to maybe give you guys some pointers on doing the homeworks. In particular, the last one from chapter 5.
By the way, I will hang out the whole time, but I'll let Jack do everything and I'll just run tech. But Jack, I am recording this class. It'll wind up on
Okay.
YouTube. If that's okay with you.
Yeah. Just, yeah. If I run out of steam, Walter, maybe I can have you take over, but
yes, sir.
We'll see how it goes. So I see you.
Yep. That's why I have two computers. I wanted to wave at everybody on the last day of class. Because I miss all of you.
Yeah. All right. Okay. So lower hand. Okay. So Issa, does that mean you have a question?
Yeah, I just didn't want to interrupt you.
Yeah.
I was gonna ask if we end up doing some example problems, would it be possible for you to go over a little bit how to approach the problems? Because a big issue I have personally is looking at the problem and understanding what I have to do and kind of getting the ball rolling.
Mm-hmm.
I don't know if that makes sense.
Yeah. No, that does make sense. So, I mean, let's go through some of the homework 7 or the chapter, sorry, this is chapter 5, homework 7, chapter 5 problems. Because I see there seem to be a lot of misconceptions. Plus, this is kind of the bread and butter of quantum physics. So the first problem number 63 or 68, sorry, asks. Let me open up the book, actually. Just to get the right statement of the problem. Okay. So to describe a matter wave, does the function a sine kx times cosine omega t have a well-defined energy? So let me actually write this down. So psi of x and t. And I haven't figured out how to erase yet without erasing the whole thing, so I just have to not write any mistakes. A sine kx cosine omega t. So this is the wave function. And the question does it have a well-defined energy? Okay, so this is the type of problem, maybe, Issa, that, trying to figure out whether it makes sense. Although I see you, or how to figure this out.
Yeah.
So what does it mean? Sorry?
Yeah, nothing.
Okay.
Yeah, go ahead.
So what does it mean for this to have a well-defined energy? Anybody? Feel free to type. How can we? Okay, f and f prime are continuous. Okay, well those are usually things that we want, but right, a constant times the original function, right? We want this to be an eigenvalue, a solution of the eigenvalue problem. So when we apply what that means is when we apply a particular operator to this, in this case the Hamiltonian, we want that to return E psi, right? We want H psi to be equal to E psi. So what that means is when we apply an operator, in this case the Hamiltonian, to the wave function, it will return a constant times that original wave function. Okay. Okay. And so then, what is the energy operator? What is that Hamiltonian? Assume this is for a free particle, so there's no energy, or excuse me, there's no potential. Then in that case, that H is going to be equal to I H bar partial T, right? In other words, that's the thing that's usually on the right-hand side of the Schrodinger equation, the time-dependent Schrodinger equation. And so that's the Hamiltonian operator. And so now we're just going to apply that to the original wave function. And what happens when we do H psi? That's going to be equal to I H bar A times what? Okay, I guess it's not so easy for you to respond, for you to type an equation. So this is going to be minus H. Yeah, so let's see here. So the question, which is a good question. So H, you're right. That's the Hamiltonian. Well, let's apply that and see what happens. Yeah, so that's a good point. So let's apply minus h bar squared over 2m, which is just a constant, partial squared, partial x squared, the psi. Okay, so if we do that, then that actually is, let's see, so what will that do? That will give us two derivatives basically on the kx term. So let's do partial psi partial x equals ka cosine kx cosine omega t, and then partial squared psi partial x squared equals, k squared minus k squared a sine kx cosine omega t. Okay, so if we apply that, then we do get back the original wave function times a constant. So I believe that this actually is an eigenvalue of the original equation and has a well-defined energy. But if I were to take, let's see, I think I maybe, Yeah, so I think that this is okay. I just have one nagging question in the back of my mind, which I don't want to deal with online here, but I'll maybe get back to you on Thursday. But I think that's the gist of it. And so, yeah, so this is equal to E psi. So this really does have an energy eigenvalue.
Jack, just as a note, there is no class Thursday. This is the last class.
Oh, this is the last class. Okay.
Yeah.
All right. That's good to know.
Sorry.
No worries. No worries. That's good to know. That's good to know. Sorry, I'm still a little out of it. Okay. The next problem, problem 78. Okay, so there it's verify that the normalization constant, so you're given a wave function, and here, may I erase this? Okay, so you're given some new wave function. So 2 square root of a cubed x e to the minus ax. This is for x greater than 0, and it's 0 for x less than 0. Okay, and so verify that the normalization constant is correct. Okay, so the way you would set this up is you would integrate, well, the integral from minus infinity to 0 is very easy, right? What's that? That's just going to be 0. So we're going to integrate from 0 to plus infinity, 2 square root of a cubed x e to the minus ax dx. And this, you could either look it up. Oh, by the way, that's not right, because this is the normalization constant. That's fine. Except, or this whole thing is psi of x, and what we really want is psi of x squared, right? We want the integral of psi star of x, psi of x dx from minus to infinity to be equal to 1 equals, and this is just, psi squared dx minus infinity to infinity. Okay, and so good. So what we really want is this whole thing squared, and that's a real number. There's no complex. There's no I in there, so we can just square it, in the usual way. So we'd have a 4a cubed x squared e to the minus 2ax dx. Okay. And so then, you can look this one up, or you can do integration by parts. And I mean, I did integration by parts. And if you do this thing out and you don't make any math mistakes, then you find that this thing really is equal to 1. And so this checks out. And it looks like most of you actually understood this. I figured this one out. The next one, 79. This one actually, so sketch the wave function. Is it smooth? So I have to erase this. Sketch the wave function. So this thing starts off at x and then drops like e to the minus ax. So it looks something like this, right? This is x, and this is psi of x. So I guess so. Some people got tripped up on what does it mean for something to be smooth. Okay, so I Googled it just to make sure I had the right um, definition. And typically, what it means for this to be smooth is that it's continuous and the first derivative is continuous. Okay, and so is this thing continuous? Well, basically, this function has to be 0 at 0. So psi of x, because psi of x less than 0 is 0. So at 0, this thing has to hit 0. Well, of course it does, right? Because e to the 0 is 1, and then x times x, which is 0, is 0. So psi of 0 equals 0 from the left and from the right. But how about the derivative? So what is the first derivative of this thing at 0? So the derivative of as it approaches from the left, that's just going to be 0 because it's a constant. But as you approach it from the right, so psi prime of x is equal to, so you've just got some constant, and then you've got e to the minus ax minus ax e to the minus ax, which is not very easy to read, minus ax here in the exponent. Okay, and so what happens when we set x equal to 0 here? This term will go away. This term here will go away, but this term will go to 1. And so then this term, so psi prime of x from 0 as it approaches 0 from the right is going to be equal to 2, the normalization constant. And so the first derivative is not continuous. And so then I would say from the definition of smooth that this is not smooth. Not smooth at x equals 0. But everywhere else it is. Okay, so that was what we were looking for. Any questions on this? Okay. I don't see any questions as people are typing. And then problem 80. Determine the particle's most probable position. So how are we going to do that? So the most probable position, so there are a number of things, right? There's the mean position, the root mean square position, but the most probable position is going to be obtained. We can get, yes, so it's the average of the probability amplitude. That's right. And since this is a real function, that we could take d psi squared dx, or we could just take d psi dx, because the square of the thing, as long as it's positive, which it is, it's a positive function, or 0, then d psi dx, we could do this, and then set that equal to 0, and figure out what x is. I just use the fact that psi will have the exact same maxima and minima, and it was just slightly easier. Again, that's 2a cubed. Let's see, so we'll have e to the minus ax minus ax e to the minus ax. And so then I want to set that equal to 0 and then solve for x. Okay, so I'm going to pull out all the constants. and I'm going to pull out an e to the minus ax. And so then I get a 1 minus ax. And so the exponential doesn't have anything to do with this unless I send x to infinity. But that's not going to be the most probable position. That's where the wave function drops off to 0. So I can just divide this guy, these terms out, and now I just have a very simple function. So I just have ax equals 1, or x equals 1 over a, which, again, most people got. Okay, then 81, looks like most people got that too. What is the probability that the particle would be found between x equals 0 and x equals 1 over a? I'm not going to do the whole thing. I'm just going to set it up. So you want the probability that the particle will be found. So we want, so we just want the integral of psi squared dx within the range that's specified from 0 to 1 over a. And so then it's just a matter of plugging in psi, squaring it, and carrying out this integral, which requires some integration by parts. But this is going to end up being 0.323 approximately. So it's about a third. The probability is like 1 in 3 that it'll be between 0 and 1 over a. Okay. Am I going at the right speed? Are people getting this? Okay. Okay, good. All right, next one. Problem 82. Calculate the expectation value of the position of the particle. Okay, so now this is the mean value of x. So this is what we sometimes write as this. And so this is going to be the psi star x psi dx. And we're going to integrate from minus infinity to plus infinity because we want the full range. And so what this just ends up being is the integral. So we get the 4a cubed. I can pull out the x, and then it's just psi squared. So, well, the 4a cubed times x squared, so this becomes x cubed, e to the minus 2ax dx. And so then I just want to integrate this thing. And so this is just going to be an integral by parts, which most of you actually did. And if I, what's it? Okay, sorry. Hang on. For some reason, your message. Okay. Okay. Good. I'm getting your messages now. Okay. Okay. What's the difference between expectation value in 82 and the most likely position like in previous problems? Okay. So the expectation value is what happens, is this thing here, where we basically multiply the probability by x. And so this is basically giving us a weighted average of x. Okay. So this is sort of what we mean by the average, right? It's you add up a whole bunch of things. And so you could imagine, like, the test score distribution, right? If you have a bunch of quizzes that if you wanted, you could do a weighted average. You could figure out what the average score was. And that's basically what this thing is. But that might not necessarily be the same thing as the most likely grade, right? Everybody might have got, a large fraction of the class might have scored an 8, say, out of, a quiz from 1 to 10. But the mean could be something else, right? It'll probably not be an exact number. Whereas the most probable one is one of the is just what the greatest number of people got. And so the most probable value is the thing you can picture on the graph most easily. It's the peak of the wave function, or the peak of the square of the wave function. So that's the difference between the most likely value and the average value. Okay, then ISA, I'm not sure what mode is, but yeah, the average value is the mean. I can Google mode. Mode versus mean. Okay, so the mean is the average. The mode is the value that occurs most often. Okay, yeah, so the mode, yeah, so you're right. That would be the mode. Yep, okay, very good. Yeah, and then Isa asks, how do we get an x cubed? So the point is the wave function is proportional to x e to the minus ax. So when we square this thing, we're going to get an x squared e to the minus 2x, but we're taking a mean, so that we have to weight it by a value of x. So that's going to be another power of x. And so that's going to give us the x cubed e to the minus 2ax. Okay. Yeah, this is not a this is an actual x. That's not a multiplication sign. Yeah. Yeah, I know. I mean, the expectation value of an arbitrary operator O is psi star O psi, and then integrated over all position. And so O is in general a function of x. In this case, for the position, O actually is just x, which looks just like a multiplication sign. Oh, psi star is the complex conjugate of psi. In this case, psi star just is psi, because psi is the real function. I mean, if psi, suppose for some reason psi was x, not normalized, but was x e to the minus I ax. Okay, I mean, for whatever reason, this might not actually solve, the Schrodinger equation, but let's just suppose that this was your psi. Then when you did psi star, you would end up with e to the I ax. That's right. Well, when psi is complex, I should say. When psi has a complex part, when psi has an imaginary part, yeah. But it can in general, and so you do have to worry about that, which is why that's the sort of general notation. Okay. Okay. Good. All right, so on to the next one. I mean, I didn't actually do the calculus on this, but I think most of you, that isn't where your issues lie. Okay. So next one, problem 83. calculate the uncertainty in the particle's position. Okay, so here we need the uncertainty. So the uncertainty is defined in this way. Okay, and so we need to get, so we just did, well, if we did the whole problem, we would have just calculated expectation value of x. But now we need the expectation value of x squared. Previous problem. And so x squared, so this is the same idea. So now it's going to be psi star x squared psi dx. And here you won't mistake it for a multiplication sign. Okay, and so then you're going to end up again with your 4a cubed. But now you're going to have an x to the fourth e to the minus 2ax dx. And again, this is from, okay. Yeah, put one on for me too, Walter. 0 to infinity. And so we could do this, and then we would end up, it turns out to be 3 over a squared. And the previous problem, this thing turned out to be 3 divided by 2a. And so that means that delta x, so this is the standard deviation, right? This is, yeah. So this is going to be, so you'll have a 3a squared minus 9/4 a squared. That's a 9 square root. And so then this will be 12/4 minus 9/4, so that'll be 3/4. So you'll end up with a square root of 3 over the square root of 4, which is just 2. And then there's an a down here. Okay. Any questions on this one? Okay. All right. So then on to the next problem. So problem 84, determine the expectation value of the momentum of the particle. So now we want this. And so as per usual, it's just going to be psi star p psi dx. But now it matters that we put this thing in the middle, right? So the operator gets sandwiched in between the psi star and the psi. That didn't matter before because it was just x, which is just a number. But in general, these things are operators. And so p actually has a partial derivative in it, right? So p is equal to minus I, so p hat is equal to minus I h bar partial x. Okay, so that means that the expectation value of p is going to be, so we can put the psi star, so we can factor out the constant. So there's this 4a cubed, and then I'm going to write x e to the minus ax, and then I have my minus I h bar partial x times x e to the minus ax dx. Okay, from 0 to infinity. And so then I can take my partial derivative. I have my minus I h bar. So this thing becomes e to the minus ax minus ax e to the minus ax dx. Okay. And so I'm just going to end up with something which is proportional to x squared and x. I mean, I can work out the algebra of this, and then do the integrals, and they're the same integrals that I've already done in previous problems, in some of the previous problems. And so when I work out the algebra and the calculus, this all ends up being 0. And so it says explain. So what this means is that the particle is equally likely to be going one direction versus the other. So it doesn't actually pick out a particular direction of motion. Oh, how do we know to go from 0 to infinity? The reason is because the wave function for x less than 0 is equal to 0. Right? Because, I mean, that's just that's just the definition of the wave function. And so it's only non-zero from 0 to infinity. And so to get the expectation value, we want to integrate from minus infinity to plus infinity. But we're taking into account the fact that the wave function is different when it's less than 0. It's just 0. Does that answer your question, Isa? Okay, good. Okay. And then calculate the uncertainty in the particle's momentum. So as usual, so would it matter if we included down to, so if we included down to negative infinity, you just have to remember that it's a different function once you get below 0. And so you would just divide it up into 2 integrals. One where it's 0 everywhere up to 0, and then the other one where it's that function. So in principle, you're actually supposed to integrate from minus infinity to plus infinity. It's just I implicitly did the negative or the negative real part of the line because that's 0. Ava, is the only time if we're calculating the likelihood of the particle being in a, that's right. That's right. So if you're doing expectation values of the mean or of momentum or position or whatever, then yes. Then you want to integrate from minus to plus infinity. But if you want to know the probability of it having a particular range of, of the particle being in a particular range, you just integrate the square of the wave function over that range. So yeah, so that's right. That's right. So these expectation values generically are over the whole integral. We want to get, for example, p or p squared or x squared. And in fact, the next problem 85, asks us for p squared. Ethan, yes, it is being recorded. Okay, so p squared. So this, generically, again, from minus to plus infinity, is going to be psi star p squared psi dx, which is, in our case, so we've got our 4a cubed x e to the minus ax. Now p squared is going to be minus h bar squared partial squared partial x squared, and then x e to the minus ax dx. Okay. And so this partial squared partial x squared operates to the right, and so then you have to take two derivatives of this thing. All right, so you're going to want partial squared partial x squared of x e to the minus ax. And then you're going to plug that into the integral. Yes, that's right, because p, that's right, Yanju, because p equals minus I h bar partial partial x. And so when I square this, I get that minus sign. Yeah. Minus I squared is not 1, because you can break it up into two pieces, right? Minus 1 times minus 1 is plus 1, and I times I is minus 1. So I squared is minus 1, but minus I squared is also minus 1. Yeah. Okay. And so then I can do this integral. And if I do it out in its full glory, which is like 6 or 7 lines, I end up with h bar squared a squared. And most of you did do this. And so then if I want the uncertainty in the momentum, right, that's delta p, and that'll be my square root of p squared minus p, quantity squared. And so what was p from the previous problem? That ended up being 0. And so that means that this thing is just the square root of h bar squared a squared, which is just h bar a. Okay. And so then, what is the product of delta x and delta p? How does it compare with the minimum theoretically possible? Okay. So, first of all, what is delta x? What is delta x, delta p? So delta x we calculated was the square root of 3 over 2a. And delta p is h bar a. Okay, well that's good, because this thing should be proportional to this thing should have units of h bar. So a is units of 1 over distance, so that cancels. And so this is the square root of 3 over 2 h bar. So what do we know from the uncertainty principle? That delta x times delta p has to be greater than or equal to. Anybody? Yeah, so h bar over 2. And is square root of 3 over 2 greater than 1 over 2? Yes. So this thing is smaller than our answer. And so that means that it satisfies the uncertainty principle. So that's good, right? When do we get h bar over 2? What is the special solution where we happen to get h bar over 2? When does that hold true? It turns out that happens when we have, when we have a Gaussian, right? So when the wave function is proportional to e to the minus, well, bx squared. It turns out if you do this, we can make it equals if I just give it some normalization to make it correct, whatever big A is. If you did this thing, if you calculated delta x and delta p for this wave function, which happens to be the ground state of the harmonic oscillator, if you took this, this would end up being h bar over 2, the delta x delta p. So this has the minimum uncertainty. But typically everything else will be greater than that. So remember, the uncertainty principle is only an inequality. It only tells you how, your measurements can only be so good, and that gives you sort of a lower bound or an upper bound on how good your measurements can be, or a lower bound, on how small your errors can be, or the product of your errors. But they could always be bigger, right? You could always do a crappy experiment and get worse errors, or the wave function doesn't have to be the minimum uncertainty wave function. And so you might end up having even more uncertainty. Okay. But that's just,
So Jack,
with a sorry, question?
Jack, legit question. This is Walter, actually.
Hi, Walter.
Is it true that only Gaussian wave functions have that minimum uncertainty?
Well, that's a good question. I know it
I
is.
think so.
I don't know of anything else that I've ever seen that gives it.
Yeah, I think you can prove that, but I haven't thought about that in a long time.
Yeah. Yeah, my intuition on this is that or my dim recollection is that that's the only one.
Mm-hmm.
But yeah.
We'll make Matthew go prove that he's better at math than I am.
Yeah. So anyway, yeah. So that's something you guys, when you're done with your finals and you're quarantined over the summer, you want to try and figure out. I leave that as an exercise. Okay. It's good. I'm glad somebody appreciates my sense of humor, although I was being serious. All right. Okay, and one more, problem 87. The particle has E equals 0. Show that the potential energy for x greater than 0 is given by U of x equals blah. And so then the idea, so if this has energy 0, so then the point was, let's just plug this into the Schrodinger equation. So this is the position second derivative of psi plus energy psi equals E psi, right? This is the time independent Schrodinger equation for psi. And we know what psi is. And in fact, and we know that we just said that E was 0. So basically, we're just going to plug psi into this formula and solve for U. And most of you did that, and I don't know that it's worth going through the algebra / calculus to get through it. But that's, you guys know how to differentiate a function and do the algebra, and you've shown me that you do. So that's how that one works. So solve for U. Okay, so that takes me through all the problems from this homework. Okay, when do we know to default to the Schrodinger equation? Well, so yeah, so in this case, how do you know? I guess the statement is, we're assuming that this psi, if this psi actually is a wave function, that this is a solution to the Schrodinger equation. But we didn't know what the potential was that happens to give this solution. And we didn't know the energy for that matter. But if somebody told you the energy was 0, then this problem shows that you could infer what U was in order for this psi to actually satisfy the Schrodinger equation. Yeah, so all wave functions should satisfy the Schrodinger equation. That's the point, that psi of x, or psi of x and t, psi of x should satisfy the time-independent Schrodinger equation, and psi of x and t satisfies the time-dependent one. Yeah, so these probability distributions, it's kind of like, in Newton's laws, you want to know what the trajectory of a particle is. You want to know what its x of t is. And so somebody gives you some x of t. But where does that come from? Well, where that really comes from is F equals ma, which is a differential equation, right? Because a is just d squared x dt squared. And then F is whatever F happens to be, sum of the forces. And so presumably that trajectory comes about from solving Newton's law. Sorry, my screen I locked me out. I've got the screensaver on too short of time. Yeah, and so x of t is just the trajectory that solves Newton's laws, and so then you can use that to figure out where the particle will be for at some future time. Well, the Schrodinger equation gives you the wave function, and then once you have the wave function, you can calculate the probability of finding the particle at a particular place. You can calculate the expectation value of basically its mean position, the error in its position, its mean momentum, the error in the momentum, the uncertainty in the momentum. So you can calculate all that stuff. So typically the way this thing starts is you're given the Schrodinger equation, you're given a particular potential, which is like giving somebody, giving you the force. And then you solve for psi of x, and then you use psi of x to figure out the properties of the system. Except instead of saying this is where it's gonna be, like in a particle trajectory, you figure out the probability of it being in a range of values. In this question, you're given psi of x. So this is kind of like, suppose somebody gave you the trajectory and then asked you things like, where is it going to be at time t equals 5 seconds? So this wave function, you'd never had to look at the Schrodinger equation. It's just calculating expectation values. But supposing it did solve the Schrodinger equation, what would the potential have to be? So that it comes sort of full circle on this last problem. So yes, in this question we did it backwards. Very good. Okay, so I just got through all of the problems. I don't know if there are other questions. Sort of generic questions on this, our last class. I decided, so I put up the last homework due Friday on the course homepage. I also put up an extra credit assignment, which is the particle physics of chapter 12. I'm not going to have a lot of time. I don't know if I'm going to have any time to talk about it. But you can read chapter 12, and the problems there are pretty self-explanatory, and at any rate, they're extra credit, so it's optional. I was thinking of making them worth half a point each. If the final exam is out of 100, then they'll be half a point each, and there's something like, I forget how many, 8 problems maybe. So it's potentially 4 points on the final. That's what I did last year. No, just chapter 12 is the extra credit. Chapter 6 is like any other homework assignment. And both are due Friday. Although actually, I could make the particle physics one due at the time of the final. actually, maybe that gives you a bit more time and a little less pressure. But yeah. So my hope is to get you the exam by Friday. Walter
By
and I
this
have to talk about what we're going to do.
Yes.
Yeah.
So Jack, when did you say their homework assignment was due?
The homework chapter 6 is due Friday.
So students, would you like I may be able to like run an office hour for that. If any of you would like to pop in and talk to me about stuff. Okay, so the physics clinic is open for you all. You all can go to the physics clinic, but I will like look at my schedule, figure out when I can do a maybe 3-hour office hour block. Because I'm doing a bunch for 211 too, so I have to I have to look at the 211 schedule. But yeah, I can set something like that up before Friday. Does that work, Jack?
That works. That's great.
Okay. Let me figure out when that'll be.
Are there any other questions? I don't know, unless Walter has something to say, I might call it short. I'm starting to get a little out of breath.
Well, do you have any questions about the next homework set? So I don't have the homework, I don't have the book, but if you all want to ask me stuff about the next homework set now, feel free to do that. Or you can tell me what the problems are and we can talk as a group about how to approach them. Would you all like to do that?
Yes.
Lisa, I appreciate your assertiveness. So my I know you're going to be an officer, which is a bit different, but my partner's stepfather is a drill sergeant, or he was a drill sergeant in the Marines. And he at one point, and she is not. Her grandfather is an admiral, so she's not a stranger to military culture. But at one point, he put on his, just for show, he put on his drill sergeant hat and started doing the drill sergeant thing to people around the house, and she said it was terrifying. Oh, so I appreciate your assertiveness in communication. I'm thinking of you being in charge of.
Well, thank you. Good to know someone appreciates.
No,
Issa, some people just find it annoying.
No, it's amazing. In 211 TA meetings, I wish everybody would speak up as much as you had. So let's see. People, I think Jim has just sent me is that what you sent me on Slack, Jim? Okay. So which problem is that? Question 13. Okay, so question 13 says, yeah. Okay, so let me push a few buttons and share. So this is actually, this is a really good problem for you all to do. Let me get a thing that I could write on. Stand by 1 sec. Screw it. Okay, so you all can see a piece of paper now?
Yes.
All right. So question 13 says, show that a prime e to the touchscreen glitch e to the ikx plus b prime e to the minus ikx equals a sine kx plus b cosine kx if a prime equals b minus ia and b prime equals, oh, there's a 1/2 there, 1/2 b plus ia. So Jim, you asked about this one. What are your thoughts on it? Like, what are we even looking at here? First of all, who cares? Why these functions? Are these functions even anything we should waste our brain power thinking about? Like, what are we doing here? Okay. So here is, I would try to draw some things in 3D, but I will be bad at it. I want to talk about two kinds of functions that we encounter all the time and that are super important, but that we never tell you about. This is one of the things in education research is finding hidden curriculum and unhiding it, like things that you expect students to know, but that you never actually talk about directly. Yeah, they kind of look like conjugates. Yes, you will use Euler's formula. Remember Euler's formula. And Jack, if you're there, feel free to chime in. E to the I theta is cosine theta plus I sine theta. So there are two sorts of functions we see a lot. One is f of x equals, how shall I write this? E to the ix, or ikx. And this is, well, tell me about this function. What does this look like? Tell me its properties. Okay, you've told me what it equals. So yes, Nicholas, you've used Euler's formula and you've told me what it equals, but it's what this function, how this function varies with x is perhaps more illuminating. So we, again, like the way to visualize complex values is on a the complex plane. So Jack, are you still there?
I'm here, yeah.
So this function in here, I am going to badly mess up. Yes, Nicholas, that is exactly right. This function draws a unit circle in the imaginary plane as you increase x. So this function here is an oscillatory thing. It is an oscillating phase. So one way to think of this is, I'm going to draw things in red here. Oh, it's not quite a circle. And you get the idea. This is going like this in the imaginary plane, where at each point you have a vector like so, right? And this point here is f of x. So e to the ikx is an oscillating phase in the complex plane with magnitude 1. So that sort of function is commonly encountered because often when we're doing both quantum mechanics, but also electrical engineering or anything that involves frequencies, often we want to separate out the part of a function that tells you about its magnitude and the part of the function that tells you about its phase. So whether it is real or complex or things like that. Isa, I want to respond to your comment in a minute. So what this is f of x. So often you will see something like, so this may be complex. You might write this as some real part multiplied by e to the I theta as a function of x, and this tells you its phase. And this is a really, really common way to represent functions. So let's think about what's going on. Let's think about what this term is on the complex plane. So if suppose k is positive, so if I write e to the ikx, does that rotate clockwise or counterclockwise? Counterclockwise, yes. So in our complex plane that the problem wants us to imagine, you've got two functions here. One rotating this way, right? This is e to the ikx. And then you have another one rotating this way, which is e to the minus ikx. So if you add, so let me now ask you kind of a warm-up question. So suppose I ask you what 1/2 e to the ikx plus e to the minus ikx is. Where would that be on our complex plane? So notice the 1/2 of the sum of things is just the average. It would be on the real line. Yeah, exactly. So if I were to average those 2 points together, so average together this point and this point, I would wind up with this point. And as k gets bigger, this would just go back and forth like this, right? You can't really see what I'm doing, but I'm moving my cursor back and forth, right? So that would go this way, right? So do you know any functions that oscillate back and forth on the real line? Sine and cosine. Exactly. So this is actually equal to cosine kx, which you can see with Euler's formula. So complex exponentials then give us another way to represent oscillatory things. And often in the mathematics that you deal with when you're dealing with Fourier analysis or other sorts of oscillating whatnots, is you need to translate back and forth between the complex exponential way to represent oscillating functions and the sine and cosine way to represent oscillating functions. Again, A and B here might not be real. But I think what the problem is imagining is they're saying, okay, this is the most generic, real oscillating thing I can think of, right? A times sine plus B times cosine, that's a kind of generic sinusoidal but purely real function, right? And what this problem is doing is they're saying, how do I take this most generic, purely real oscillating function and express it as complex exponentials? I sort of already did this, right? I sort of already showed you that a single cosine could be written this way in terms of complex exponentials and have the imaginary part cancel out, right? Between the red arrow rotating counterclockwise and the blue arrow rotating clockwise. But here we want you to do this with a more generic oscillating function. Does that clarify what that problem is about, James? Okay. Any other, anybody else want to make a comment about this, like how you go about it or anything? Okay. Anything else you all want to talk about?
There's a question on there about why we can substitute alpha I for k prime. Could we talk about that?
Yes, we can. Yes, we can, and I can stay after 1:50. But before everyone has to go, I'd like to announce the office hours I will be running will be Thursday from 1 to 4 p.m. So is there anybody for whom that time is just a disaster? Okay. So Thursday from 1 to 4 p.m. is 361 office hours. What was your other problem you wanted me to comment on, Issa?
It's, I don't know if the number helps, but it's 28A, but it just says that for the, it's more of a conceptual one, sorry. There's a lot of pages in this book. So reflection and transmission probabilities can be obtained from equation 12, which is an equation with a bunch of k's and k primes in it. I could pull up the page if you need it, but it says the first step is substituting negative I alpha for k prime. Why can we do that?
Substitute minus I alpha. So is there any clarification on what alpha is?
Yes, alpha is...
Yeah, this is, Walter, I think this is going from, hang on, is this for this is for transmission?
Oh,
Yeah.
and reflect.
So,
Yeah.
so it's switching from E less than U to the other way around,
Got it.
vice versa.
Got it. So yeah, here's what this is. So, and I think this is an issue of notational confusion. I used kappa where your book uses alpha, because I again, I don't have your book, right? I was teaching from like what I had learned. And remember we said that K was square root 2m E minus U over h bar squared. So this is, this corresponded to an oscillating function. Right? But then we asked what happens if U is greater than K. So we saw if U is greater than E, then K becomes imaginary, right?
Okay.
And then so our heads wouldn't hurt. We defined kappa as like basically an imaginary wave number. Remember this?
Yeah.
And that's fine. That's all well and good. That worked. But these two things are really equivalent, right? Because you can show that e to the ikx here, that's exactly the same as writing e to the kappa x. Well, actually, yes. Since after all, kappa here is just ik,
Okay.
right?
Yeah.
So what this problem? Oh, go ahead.
Yeah, because alpha is just kind of equal to the same thing as the K that they have in there. I think I remember that. So it's just adding the I because it needs that imaginary component to it.
Yeah. So let me phrase it in another way. So what you've got, right? Here's your potential step, right? Or who knows what it is that you had? I guess it was this. And you had, if this is your energy, right? If this is your energy, whoops, I want one higher. So if you have an energy that's greater than the potential, then you have oscillatory wave functions on both sides. Oscillatory just means K is real, right?
Yeah.
But if you have now an energy that's less than that, an energy that's less than U, you now have an oscillatory wave function here, and here you have an exponentially decaying wave function. Right?
Mm-hmm.
And when I did this material kind of for the first time, I kind of emphasized that idea that in the region where, and I'll use the book's notation, I'll use alpha here, that where the energy is less than U, that means you have a negative kinetic energy. That means you have an imaginary wave number, but imaginary wave number just means an exponentially decaying function, right?
Okay.
This question in the book, I think, is trying to remind you that even though you kind of have these two different formulas, that they really reflect the same thing.
Okay.
There's one other thing, though, too, though. So imagine this case where I've got a potential step and the energy is less than the potential. One second. Yanju is asking how to find me at office hours. I will do office hours, I think, in the virtual clinic. So you all can write on the screen. So yeah, office hours will be in the virtual clinic on Zoom. Yeah, alpha decay is entirely something else. So if I've got this second situation where I'm throwing particles with a boundary or a barrier that's higher than them, what fraction of those particles do you think are gonna bounce off?
A majority of them?
All of them. We did that in class. We saw that in this case, right, what you get, let me doodle it out here, you get a sinusoidally oscillating wave function, and then a decaying wave function,
Right.
and then something that's reflected back to the left. But so if we call, let's see, if A is the incident amplitude, B is the reflected amplitude, like there's a lot of complex analysis stuff that's kind of buried in here, and C is the transmitted amplitude. So here, C, remember, this is a region with an imaginary wave number. So we just said that all of the particles reflect, right? What does that tell you about B?
It's gonna have the same amount of particles as A?
Yeah, same number of particles as A. So how do I say same number of particles as A mathematically?
Is that when you square it?
Right, exactly. So what this tells you, and we did this derivation a bit ago, exactly, that tells you that their squared norms are the same. Does it mean B equals A?
No.
Right, how could they be different?
Math. I'm not sure off the top of my head.
So that's actually like one of the things, and I didn't talk that much about this. Jack, if you're here, I'd really be interested in having your input as somebody who taught at the beginning of the class. But here, remember we talked about how e to the I theta represents a number with magnitude 1, but that just rotates something in the complex plane? So what this means is that B is A with a phase shift.
Okay.
So the waves that bounce back have the same magnitude, but a different phase. So in the complex plane again, it's not at all straight. In the complex plane, if this was the incident wave, then the reflected wave might have exactly the same magnitude, but might be rotated in the complex plane.
Okay.
And one of the skills that like we don't teach directly, and maybe we should, is how to kind of wrap your head around these funny numbers that both have a magnitude and a direction in the complex plane, and then how to do math with them and how to deal with all the e to the I whatevers and make sense of them in your head, right? Because you know what numbers mean, you know what real numbers mean very well, but getting an intuitive sense of what complex numbers mean is tough. Okay. Jack, did you want to comment on any of that?
No, I actually can't hear you very well for some reason.
Oh, Isa, could you hear me okay?
Yeah, I can. I actually do have to go to Calculus 3 now, though.
Oh, of course. Sorry to keep you over.
No, it's okay. I wanted to stay as long as I could, but I'll definitely see you in office hours. Thank you, Walter.
Yep. See you. Appreciate you all. Yep, thank you, Charles. Hey, Jim, while you're here, you want to be an Ask 101 coach in the fall?